In a distant galaxy, billions of light-years from Earth, a star 100 times the mass of our Sun is nearing its end. For a fleeting instant, it will release energy exceeding that of 1 trillion suns, generating shockwaves that ripple through the very fabric of space-time. This evening, we embark on a journey into cosmic phenomena of such immense power that they warp reality. We will witness explosions brighter than entire galaxies, explore black holes that consume light, and delve into the fundamental forces underpinning the cosmos. Brace yourselves for an expedition into realms of power beyond human comprehension. Within each atom composing your very being, a hidden battle rages incessantly. Protons, densely clustered within the nucleus, should by all rights instantaneously fly apart. Their positive charges repel one another with immense force, akin to forcing together two potent magnets. Yet, inexplicably, they remain steadfastly bound by the universe's most formidable power, the strong nuclear force. This force exerts its influence at distances less than the diameter of a single proton, yet its potency is unparalleled. Scientists quantify its strength as 100 times greater than electromagnetism, and 10 to the 18th power times stronger than gravity. Consider this analogy. If gravity were a mere murmur, the strong force would be a cataclysmic thunderclap, capable of pulverizing mountains. This force acts through particles known as gluons, functioning as invisible tethers that bind quarks together, thus forming protons and neutrons. The more one attempts to separate these particles, the more intensely the force resists, much like stretching a rubber band that thickens and stiffens with each incremental pull. This unusual behavior, termed confinement, dictates that isolating a lone quark remains impossible, regardless of the energy applied. Inside every proton, 3 quarks perform a perpetual dance within a prison of pure energy. The gluons that bind them carry the strong force, creating a network of interactions so intricate that even our most advanced supercomputers struggle to simulate it accurately. When one attempts to separate quarks, the added energy merely generates new quarks and gluons. It is like severing a chain only to witness the formation of new links. The strong force operates at scales so minuscule that even a femtometer, 1/4,000,000th of a meter, appears vast, dimensions far smaller than anything imaginable. At these distances, the familiar principles of everyday physics completely unravel. The nature of space and time itself shifts and wavers, subject to the peculiar dictates of quantum mechanics. This fundamental force molds the very essence of matter, dictating which atomic nuclei are stable and which are not. It governs the speed at which stars consume their nuclear fuel, and it dictates the delicate equilibrium between creation and annihilation within the core of every star scattered across the vast cosmic expanse. Were it not for the strong force, protons would immediately repel each other due to electromagnetic forces. Atomic nuclei would fail to form. Fusion reactions within stellar cores would never ignite. The universe would consist solely of hydrogen atoms and unbound electrons. However, for all its immense power, the strong force possesses a critical limitation. Its influence extends only to the boundary of an atomic nucleus, approximately 110 trillionths of the diameter of a human hair. Beyond this minuscule domain, other forces assume dominance. Venture into the boundless cosmos, where distance reigns supreme, and observe the consequences when gravity and light engage in the most cataclysmic explosions ever observed. In the vast expanse of the cosmos, a beam of pure energy traverses space-time at a velocity approaching the speed of light. For a mere 10 seconds, it unleashes energy exceeding that which our sun will generate throughout its entire 10 billion-year lifespan. This phenomenal event, a gamma-ray burst, represents the universe's most potent explosion. These cosmic behemoths originate from the catastrophic collapse of the most massive stars into black holes. We are speaking of stellar giants, each possessing 20 to 100 times the mass of our Sun, consuming their nuclear fuel at a rate that would deplete our Sun's entire energy reserves in only a few million years. When these celestial monsters finally exhaust their fusion processes, gravity asserts its ultimate dominion. As the star's core implodes, it ejects jets of matter and energy from its poles at 99% the speed of light. The collapsing core gives birth to a black hole, encircled by a disk of superheated material. Magnetic fields, twisted and amplified by the implosion, function as cosmic cannons, propelling these jets outward with extraordinary precision. The jets pierce the dying star with the ease of a bullet through paper, emerging as intensely focused beams of destruction that maintain their tight collimation across immense distances. Imagine a laser beam retaining its focus on a journey from Earth to the nearest star. These jets achieve a similar feat, but on scales millions of times greater. A single gamma-ray burst can outshine 1 trillion stars. Were we capable of perceiving gamma rays with our eyes, these explosions would appear brighter than the full moon, even from galaxies billions of light-years distant. The energy released in mere seconds surpasses the combined yield of 10 trillion hydrogen bombs, detonating every second for the entire age of the universe. The most powerful gamma-ray burst ever recorded, nicknamed the Boat for brightest of all time, occurred in October 2022. Its intensity saturated gamma-ray detectors across our solar system and produced detectable alterations in Earth's upper atmosphere, despite originating from a distance of 2 billion light-years. Envision observing a flashlight beam from Alpha Centauri, appearing as luminous as a car headlight. This provides a glimpse into the unimaginable power of these events. The light we detect has journeyed for billions of years, conveying news of stellar deaths from a time when the universe was young, and stars were far more massive and violent than any we observe today. Scientists have detected bursts so distant that their light commenced its journey when the first stars were forming, less than 1 billion years after the Big Bang. These ancient signals offer us glimpses into the early cosmos, a period when massive stars lived fast and died violently, enriching space with heavy elements crucial for subsequent generations of stars and planets. Yet even these titans pale in comparison to the enigmatic phenomena lurking within the intergalactic darkness. At the heart of our galaxy resides a behemoth 4 million times as massive as the Sun. Sagittarius A, a voracious entity, consumes all that strays too near, from gaseous nebulae to complete stellar systems. However, this giant is dwarfed by the true titans inhabiting the cosmic abyss. Certain supermassive black holes possess the mass of 40 billion suns, compressed into a space smaller than our solar system. They are akin to cosmic vacuum cleaners, wielding gravity so intense that nothing, not even light, can escape their event horizons. Space-time itself bends around them, like water swirling down a drain, creating distortions we directly observe, defying the imaginable. These gravitational leviathans did not develop gradually. The most distant quasars radiate from a time when the universe was younger than 1 billion years, fueled by black holes that somehow attained billions of solar masses in what is, cosmically speaking, a mere instant. The mechanism behind this phenomenal growth remains one of astronomy's greatest enigmas. Standard stellar evolution offers no explanation. A leading hypothesis, posits that these giants originated as massive seeds, formed directly from collapsing gas clouds in the early universe. Unlike stellar mass black holes born from dying stars, these primordial behemoths may have harbored hundreds of thousands of solar masses from their inception. This head start enabled their rapid growth through the consumption of surrounding matter and mergers with other black holes. As gas spirals into a supermassive black hole, friction heats it to millions of degrees. The resulting accretion disk radiates brighter than 100 billion stars. Its rapid rotation propels matter near the inner edge at a significant fraction of light speed, producing time dilation effects that would stretch seconds into hours for distant observers. The most luminous quasars, powered by these ravenous black holes, are visible across the observable universe, acting as cosmic lighthouses, broadcasting their presence across billions of light years. Their brilliance eclipses that of their entire host galaxies, rendering the combined light of hundreds of billions of stars comparatively dim. The most violent black holes launch jets of particles at near light speed, creating beams that extend for hundreds of thousands of light years. These jets carry enough energy to reshape entire galaxies, heating gas clouds to millions of degrees and hindering star formation across vast cosmic regions. This energetic activity can persist for millions of years, continuously infusing their surroundings with energy. Recent observations have uncovered black holes seemingly too massive for their host galaxies, violating the typical correlation between central black hole mass and galactic properties. These excessively massive giants challenge our understanding of the co-evolution of galaxies and their central black holes. Yet even these titans yield to forces operating on scales beyond our comprehension. Across 13.8 billion light-years of space, an invisible force is engaged in a cosmic struggle. Each passing second witnesses galaxies drifting further apart, a stretching of space-time itself. This enigmatic force, dark energy, constitutes 70% of existence, yet its nature remains largely unknown. Unlike gravity or electromagnetism, its influence does not diminish with distance. On the contrary, as space expands, more dark energy seemingly materializes to fill the void. The universe's growth thus fuels its accelerated expansion, akin to a cosmic accelerator perpetually increasing its speed, relentlessly pushing everything asunder. Scientists stumbled upon this force while investigating distant supernovae in the 1990s. Expecting a deceleration of the universe's expansion due to the gravitational pull of its matter, they discovered the opposite. Space expands faster now than billions of years ago, as if an unseen force is relentlessly pulling everything apart with ever-increasing strength. Imagine a balloon inflating with an invisible breath. Dark energy is that breath, causing every point on the balloon's surface to recede from every other. Galaxies, like vessels on a swelling ocean, are borne along this expanding space, unable to resist the current that carries them into the cosmic abyss. The universe's dark energy content increases with spatial expansion, seemingly violating the conservation of energy, a cornerstone of physics. However, observations consistently reveal a constant energy density of dark energy, despite the expanding volume of space. The origin of this additional energy remains a complete mystery. Current hypotheses posit dark energy as an inherent property of space itself, a cosmic constant initially proposed by Einstein, later deemed his biggest mistake. Alternatively, it might be a dynamic field, evolving over time, or even indicate that our grasp of gravity needs significant revision on cosmic scales. The implications of dark energy are profound and alarming. In the distant future, It will dismantle everything visible. Initially, galaxy clusters will fragment beyond recognition, becoming isolated islands in an ocean of expanding darkness. Subsequently, individual galaxies will lose their cohesive structure against the cosmic expansion. Ultimately, even atoms may be ripped apart, an event scientists term the Big Rip. Stars will fade, planets will wander from their suns. Even the fundamental particles comprising matter will be separated by immense distances. Dark energy, seemingly benign today, will become the universe's ultimate destroyer, unraveling the structure gravity and other forces spent billions of years building. Envision compressing a mountain to the size of a sugar cube. Even then, its density would be 1,000 times less than that of a neutron star. These celestial beacons cram the mass of our sun into a sphere merely 12 meters across, generating gravitational fields so potent they distort light itself and contort space-time into geometries defying comprehension. Yet, gravity is not their most fearsome attribute. Neutron stars boast magnetic fields 1 trillion times stronger than Earth's protective magnetosphere. These invisible forces trap charged particles, accelerating them to near light speed, thereby creating radiation beams that sweep across space like cosmic searchlights, fueled by the universe's fundamental forces. A typical neutron star's magnetic field is so formidable it could obliterate every credit card on Earth from a distance of 600 meters. Approaching to within 1,000 kilometers, the magnetic force would be sufficient to extract the iron from your blood. The field lines themselves become visible as they capture and direct streams of charged particles into narrow beams. When these magnetized neutron stars rotate, they transform into pulsars, emitting beams of radio waves and X-rays with the precision of atomic clocks. Some spin 600 times per second, faster than a kitchen blender, yet maintain impeccable timing, rivaling the most accurate timepieces ever constructed. Each pulse signifies another rotation of a stellar corpse, whirling in the darkness. A neutron star's surface is a realm of impossible physics where familiar matter cannot endure. The magnetic field is so intense, it stretches atoms into needle-like forms, aligned with the field lines. Normal atomic structure completely disintegrates, replaced by exotic matter found nowhere else in the cosmos. Any ordinary matter falling onto a neutron star's surface would be instantaneously compressed into a layer mere millimeters thick. The gravity is so extreme that a marshmallow dropped from waist height would strike the surface with the force of a hydrogen bomb, releasing energy exceeding that of all explosives used in World War II. Certain neutron stars, termed magnetars, possess magnetic fields 1,000 times stronger still, approaching the theoretical maximum allowed by physical laws. When these objects experience magnetic quakes, their crusts fracture and shift, releasing more energy in 1/10 of a second than our sun produces in 100,000 years. These magnetic cataclysms generate colossal flares detectable across the galaxy. The most potent magnetar flare ever recorded briefly impacted Earth's upper atmosphere from a distance of 50,000 light-years, showcasing the incredible range of these stellar remnants. A magnetar's magnetic field is so powerful that it influences the vacuum of space itself, rendering it birefringent, much like a crystal. Light waves become polarized as they traverse this magnetized void, providing astronomers with direct evidence of field strengths surpassing anything attainable in terrestrial laboratories. However, these stellar remnants are merely the vanguard of nature's most extreme creations. Spanning the observable universe are unseen filaments, capable of slicing through planets as readily as wire through cheese. These cosmic superstrings, should they exist, are one-dimensional entities, thinner than a proton, yet potentially longer than galaxy clusters. They are remnants from the universe's birth, marking phase transitions within the fundamental structure of space-time. String theory posits that cosmic strings formed during the first fraction of a second after the Big Bang, a period of rapid alterations in the universe's fundamental properties. Imagine them as cracks in a frozen pond, delineating regions of space that crystallized slightly differently as the cosmos cooled from its initial state of perfect symmetry. A cosmic string merely 1 meter long would possess the mass of Earth. However, their extreme thinness renders them essentially one-dimensional, possessing length but lacking width or height in the conventional sense. They exist at the very precipice between existence and nothingness, matter and energy, reality and pure mathematics made manifest. The energy inherent within a cosmic string is almost beyond comprehension. A string stretching from Earth to the Moon would contain enough mass energy to power human civilization for trillions of years. Yet this immense energy is concentrated within a line so slender as to have no measurable thickness, making cosmic strings the ultimate expression of energy density. If cosmic strings traverse space, they create ripples in space-time itself, generating gravitational waves detectable by our most sensitive instruments. These waves would possess a unique signature, distinct from those produced by black hole mergers or neutron-star collisions, potentially allowing scientists to confirm the existence of these theoretical objects. When two cosmic strings intersect, they can create loops oscillating like guitar strings plucked by the universe itself. But instead of sound waves, these vibrating loops generate distortions in the fabric of reality, emitting gravitational waves that ripple outwards at the speed of light. These cosmic string loops gradually lose energy via gravitational wave radiation, shrinking until they eventually vanish. A loop the size of our solar system would radiate away all its energy in only a few million years, disappearing in a final burst of space-time distortion. Some scientists hypothesize that cosmic strings could function as cosmic highways, enabling faster-than-light travel through folded space. If 2 points in space were connected by a cosmic string, one could theoretically travel along the string, arriving at the destination before light traversing normal space. This would establish cosmic strings as the universe's ultimate shortcuts. Others suggest cosmic strings might be portals to extra dimensions concealed from our three-dimensional world. The strings could be fundamental objects residing in higher dimensional space, with only their one-dimensional cross-sections visible in our reality. These theoretical behemoths remain hidden within the equations of physics, awaiting discovery or refutation by future observations. 4 billion light-years from our planet Earth, a black hole, vast as our solar system, expels a particle beam traversing an entire galaxy. This jet, a torrent of superheated plasma, hurtles along at 99.9% at the speed of light, possessing the energy equivalent to 1 trillion stars, yet maintaining pinpoint accuracy across distances defying human comprehension. Quasar jets originate amidst the tumultuous environs of supermassive black holes, where space-time itself becomes a battleground between gravity and magnetism. As matter spirals inexorably inward, it forms an accretion disk spinning at phenomenal speeds. Magnetic fields, amplified by this rotation, twist into configurations storing immense energy. These magnetic field lines function as cosmic particle accelerators, funneling material from the accretion disk's inner regions into narrow beams erupting from the black hole's poles. The same gravitational forces destined to swallow everything instead propel some matter back into space at relativistic velocities, a magnetic catapult mechanism. These jets are remarkably straight, appearing as if drawn by a cosmic ruler, wielded by some celestial hand. They retain their narrow focus over hundreds of thousands of light years, traversing space with a precision that surpasses any human technology. This collimation is so precise that radio telescopes detect them as thin lines, even from billions of light years distant. The particles within these jets carry energies millions of times greater than those achievable in Earth's most powerful particle accelerators. Individual protons streak along the jet at speeds so near light speed that their relativistic mass increases thousands of times, transforming ordinary matter into cosmic projectiles of immense power. When a quasar jet points directly at Earth, we observe it as a blazar, its light brightening and dimming as the beam sweeps past us, much like a lighthouse. The brightness of these blazars can fluctuate by hundreds of times within days or hours, as turbulence within the jet creates bright emission knots traveling toward us at apparent speeds exceeding that of light. This superluminal motion is an illusion of perspective. Material traveling at 99% light speed, moving almost directly toward us, appears to cover vast distances in incredibly short times. This effect vividly illustrates the proximity of these cosmic jets to the ultimate speed limit. The most powerful quasar jets possess sufficient energy to heat entire galaxy clusters, generating bubbles in the surrounding gas that persist for hundreds of millions of years. These immense cosmic furnaces can halt the birth of new stars across regions spanning millions of light years, effectively rendering vast stretches of space barren. Recent observations have unveiled jets extending far beyond their parent galaxies, penetrating the intergalactic medium and continuing their propagation for millions of years. These ancient jets bear the hallmarks of black hole activity, from eras when the universe was younger and more turbulent than it is today. In a binary star system 30 million light-years distant, a white dwarf star is gradually siphoning material from its companion, akin to a cosmic vampire preying on stellar lifeblood. For millions of years, hydrogen gas streams from the larger star onto the compact remnant, accumulating layer upon layer, much like snow accumulating on a mountain slope. Yet this stellar snowball is nearing a critical juncture, poised to trigger one of the universe's most precise detonations. White dwarf stars are the dense cores remaining after sun-like stars exhaust their nuclear fuel and cast off their outer layers. These stellar remnants compress the mass of our Sun into a sphere the size of Earth, resulting in matter so dense that a teaspoonful would weigh as much as an automobile. Their surfaces blaze at temperatures of tens of thousands of degrees, intense enough to vaporize any known substance. The pilfered material accumulates on the white dwarf's surface, compressed by gravity into a thin hydrogen shell that gradually builds pressure and temperature. The white dwarf functions as a cosmic pressure cooker, slowly heating this stolen matter until nuclear fusion begins to smolder in the surface layers. When the white dwarf attains precisely 1.4 times the mass of our Sun, a catastrophic event unfolds. This critical mass, known as the Chandrasekhar limit, represents the maximum weight that electron degeneracy pressure can sustain. Beyond this threshold, the star can no longer withstand its own gravitational pull. The accumulated material ignites in a runaway thermonuclear explosion that disintegrates the entire star within seconds. The explosion races through the white dwarf like a flame front through cosmic explosives, transforming carbon and oxygen nuclei into iron and nickel via explosive nuclear fusion. The star literally consumes itself into oblivion. This is a Type Ia supernova, and it exemplifies one of the universe's most precisely violent occurrences. Each Type Ia supernova releases nearly the same amount of energy because they all involve the same mass of material undergoing identical nuclear reactions. This cosmic uniformity makes them ideal instruments for measuring distances across billions of light years. The explosion radiates with the brilliance of 5 billion suns, visible from galaxies billions of light years away. For weeks, a single exploding white dwarf outshines an entire galaxy encompassing hundreds of billions of ordinary stars. The luminosity peaks rapidly and then diminishes over months as radioactive elements generated in the explosion decay and release their energy. The explosion synthesizes and disperses elements crucial for life across vast cosmic regions. The calcium in your bones, the iron in your blood, and the nickel in your coinage were all forged within the hearts of exploding white dwarf stars. You are, quite literally, composed of stellar ashes scattered by these cosmic furnaces billions of years ago. The shock wave from a Type Ia supernova propagates outward at thousands of kilometers per second, heating surrounding gas to millions of degrees. The explosion can initiate new waves of star formation in nearby gas clouds, simultaneously enriching them with heavy elements essential for planetary formation. Two city-sized objects, locked in a gravitational death dance spanning millions of years, spiral inexorably toward each other through the inky blackness of space. These are neutron stars, the collapsed cores of massive stars, and their impending collision promises the most violent event in the nearby universe. A cosmic forge, crafting elements surpassing the riches of any earthly king's treasury. Each neutron star harbors more mass than our sun, compressed into a sphere a mere 12 meters across. Their surfaces, composed of atomic nuclei packed with unimaginable density, possess a teaspoonful weight equivalent to 6 billion tons on Earth. These are not ordinary celestial bodies. They represent the densest forms of matter possible without succumbing to the gravitational pull of black holes. As their orbits tighten, the neutron stars gravitationally warp each other's shapes. Tidal forces, like a cosmic sculptor's hand, stretch and compress these incredibly dense objects, generating heat that ignites their surfaces to millions of degrees. The orbital ballet accelerates as energy dissipates through gravitational waves, ripples in space-time itself, stretching and compressing the fabric of reality as they propagate at light speed. Sophisticated detectors on Earth can register these waves, even though they alter distances by less than 1/100,000th the width of a proton. In the final seconds before their cataclysmic union, the neutron stars execute hundreds of orbits per second, a dizzying whirl exceeding the speed of a helicopter blade. The gravitational waves they unleash become so potent that they carry away the energy equivalent of 3 solar masses in the mere few seconds preceding impact, exponentially accelerating their death spiral. Upon contact, a brief flash of gamma rays heralds a longer-lived kilonova explosion, a cosmic upheaval that literally shakes the universe, sending gravitational wave signals detectable from billions of light years away by instruments designed to measure the seemingly impossible. The merger forges elements heavier than iron via rapid neutron capture. In this extreme environment, atomic nuclei are bombarded with a torrent of neutrons, absorbing them at a rate barely sufficient to keep pace. This process generates unstable, neutron-rich isotopes that decay into stable heavy elements, including gold, platinum, and uranium. A single neutron star merger yields quantities of gold equivalent to several Earth masses, along with comparable amounts of other precious metals. This stellar treasure is ejected at speeds nearing 1/3 the speed of light, seeding nearby space with materials destined to become part of future planets and asteroids. The collision expels material in multiple components at varying velocities. The fastest debris initiates the gamma-ray burst, while slower-moving material forms expanding shells that glow for weeks, fueled by radioactive decay. This kilonova light, emanating from billions of newly formed atomic nuclei undergoing radioactive decay, creates a fireball radiating the combined brilliance of hundreds of millions of suns. 13.8 billion years ago, all that now exists was compressed into a space smaller than a proton. Every particle, from the minuscule quantum foam to the immense Andromeda galaxy, resided within a point lacking dimensions. This was the Big Bang singularity, the ultimate display of cosmic might, the genesis of existence itself. At this primordial instant, known physics falters. Temperature and density become infinite, rendering space and time meaningless. The universe's four fundamental forces, a unified, unimaginable power, governed reality. In less time than light crosses a proton, the universe expanded faster than light, a period of cosmic inflation stretching space by factors of billions. Space did not explode into a pre-existing void. Instead, new space was created as it expanded, carrying matter and energy. The initial temperature was so intense that even nature's fundamental forces were indistinguishable. Gravity, electromagnetism, and the strong and weak nuclear forces were facets of a single, superlative force, a state never seen since. As the universe expanded and cooled, this unity shattered like rapidly cooling glass, forces separating in phase transitions, releasing immense energy and shaping physical law. Gravity separated first, followed by the strong force, and finally, electromagnetism split from the weak force. Within the first minute after the Big Bang, the universe cooled sufficiently for Big Bang nucleosynthesis to begin. Newly formed protons and neutrons, products of cooling quarks, fused in a cosmic furnace, creating most of the hydrogen and helium we observe today. Matter and antimatter annihilated in constant bursts of pure energy, given the extreme energy density. For 300,000 years, the universe remained opaque to light. Free electrons scattered photons so effectively that light traveled only minuscule distances before absorption and re-emission. The cosmos resembled a glowing fog, energetic yet unseen. Then came cosmic dawn. Electrons and atomic nuclei combined, forming the first neutral atoms, permitting light to traverse freely for the first time. This cosmic clearing produced the afterglow we perceive as the cosmic microwave background radiation, a faint echo of creation permeating the entire sky. The Big Bang was not a spatial explosion, but an explosion of space itself, creating both time and matter, establishing the physics governing everything from quantum fluctuations to galactic formation. No event, past or present, rivals its power to create everything from nothing, establishing existence's very foundations. Yet, even this cosmic genesis might not represent the ultimate limit of power within our universe. Far beyond the spectacle of ordinary supernovae lies a phenomenon of unparalleled ferocity. When a star, 50 times the mass of our Sun, exhausts its nuclear fuel, it does not merely collapse and explode. Instead, it births a hypernova, an outburst of such immense energy that it surpasses regular supernovae by a factor of 10 to 100, unleashing energy equivalent to billions of atomic bombs, detonating each second for millions of years. These celestial behemoths are exceedingly rare, even on cosmic timescales. Only the most massive stars in the universe, spinning rapidly at their demise, can give rise to hypernovae. The confluence of extreme mass and rotation generates conditions so violently chaotic that standard stellar death mechanisms are utterly overwhelmed. Upon core collapse, a black hole forms almost instantaneously. However, the star's rapid rotation prevents a simple, symmetrical collapse. Instead, the infalling matter constructs an accretion disk encircling the nascent black hole, rotating with such velocity that it functions as a cosmic dynamo, generating magnetic fields of unimaginable intensity. These intricately twisted magnetic field lines, akin to springs stretched to their breaking point, abruptly snap and reconnect, propelling jets of matter and energy outward at 999.9% the speed of light. These jets, functioning as cosmic drill bits, penetrate the collapsing star, carrying energy sufficient to power our sun for billions of years. They pierce the star's outer layers and erupt into space, creating the gamma-ray bursts we detect from billions of light-years away. Yet the cataclysm does not conclude there. The shockwave from the jet's passage incinerates the star's interior, reaching temperatures exceeding those found in the cores of typical stars, thus igniting explosive nuclear burning within the stellar remnant. Layer upon layer of the star explodes outward in a cascade of thermonuclear devastation. Carbon fuses into neon, neon into silicon, and silicon into iron within mere seconds. The energy released by these rapid fusion processes intensifies the destruction, resulting in an explosion visible from the edge of the observable universe. A single hypernova can synthesize more heavy elements than dozens of ordinary supernova combined. The extreme conditions forge radioactive isotopes which decay over weeks and months, powering an afterglow that persists long after the initial explosion. These cosmic forges produce numerous elements essential for life, dispersing them across vast expanses of space. The most potent hypernovae can disrupt star formation throughout entire galactic regions. Their shock waves compress nearby gas clouds, triggering fresh waves of stellar births while simultaneously heating the surrounding medium, preventing further star formation for millions of years across hundreds of millions of light-years of space. Two colossal galaxy clusters, hurtling toward each other at velocities measured in thousands of miles per second, are on a collision course. Each cluster is a universe unto itself, teeming with thousands of galaxies, trillions of stars, and immense reservoirs of superheated gas, radiating brilliantly in X-ray light. Their eventual merger will unleash the most potent energy witnessed in the cosmos since the Big Bang itself. Galaxy clusters, the largest gravitationally bound structures in the universe, represent the epitome of cosmic scale. Consider the Coma cluster, for example. It houses over 1,000 galaxies, boasting a total mass equivalent to 100 trillion suns. When clusters of this magnitude collide, the energy released dwarfs the combined starlight of both clusters by millions of times. The collision unfolds slowly by cosmic standards, the clusters drawing nearer over hundreds of millions of years. Dark matter, constituting the majority of each cluster's mass, remains relatively unaffected by the interaction, feeling only the tug of gravity and passing through with minimal disturbance. However, the hot gas permeating the intergalactic spaces experiences a drastically different fate. As the clusters merge, their gaseous clouds crash together at speeds approaching 5,000 meters per second. This generates shock waves, heating the gas to temperatures exceeding 100 million degrees Celsius, hot enough to fully ionize any atom present. The resultant plasma blazes with X-ray emissions, generating some of the universe's most luminous phenomena. These colossal collisions can trigger the formation of radio halos stretching across millions of light years. Magnetic fields, distorted and intensified by the impact, accelerate electrons to near light speed. They're spiraling around field lines producing radio waves, resulting in a faint radio wave glow, dwarfing entire galaxies. The most violent of these cluster collisions can spawn bow shocks propagating outward at thousands of kilometers per second. These cosmic sonic booms compress and heat the surrounding medium, producing structures observable across vast intergalactic distances. The energy inherent in these shocks surpasses the cumulative energy output of billions of supernovae. Throughout the collision, individual galaxies within the clusters themselves undergo violent interactions. Tidal forces can strip stars from galactic peripheries, leaving behind elongated streams of stellar debris, charting the gravitational dance of the clusters. Some galaxies may be entirely disrupted, their stars scattered into the expanding halo of the growing cluster. The collision can also stimulate explosive bursts of star formation, compressing gas clouds within galaxies. These starbursts can boost a galaxy's star formation rate by factors of hundreds, creating vibrant blue regions replete with recently formed massive stars, destined for short, brilliant lives. Hidden within the quantum foam, the very fabric of reality, lies a possibility so dreadful it could obliterate everything we know in an instant. The Higgs field, responsible for bestowing mass upon all particles, might not reside in its most stable energy state. Were this field to abruptly transition to its true minimum energy, a devastating bubble of destruction would erupt, expanding at the speed of light, rewriting the fundamental laws of physics and annihilating everything in its path. The Higgs field permeates all of space, existing even within the vacuum between atoms. Like a ball precariously perched atop a hill, this field might currently occupy what physicists term a false vacuum state. It appears stable, yet it could potentially plummet to a lower energy level, fundamentally altering the very nature of reality. If this vacuum decay commenced anywhere in the universe, it would generate an expanding sphere of true vacuum, hurtling outwards at precisely the speed of light. Nothing could outrun this cosmic wave of destruction, as no information or matter can surpass the speed of light. We would receive no warning of its approach until the moment of its arrival. Inside this bubble of true vacuum, the fundamental constants of nature would be different. Particles might possess altered masses or might cease to exist entirely. Atoms, as we understand them, could not form. The strong nuclear force might weaken, causing all atomic nuclei to disintegrate instantaneously. Chemistry and biology would become impossible. The energy differential between the false vacuum and true vacuum would be unleashed as the bubble expanded. This energy could surpass the rest mass energy of all matter in the universe, rendering vacuum decay more energetic than converting every proton, neutron, and electron into pure energy. The universe would be inundated with more power than every star and galaxy combined. Current calculations suggest our vacuum might indeed be metastable, delicately balanced on the precipice of stability. High-energy events, such as cosmic ray impacts or black hole evaporation, could potentially trigger this transition. Even quantum fluctuations might spontaneously nucleate a bubble of true vacuum in empty space. The terrifying aspect of vacuum decay is its inevitability, assuming the false vacuum state exists. Quantum mechanics dictates that any metastable state will eventually decay, however minuscule the probability. Over the immense timescales of cosmic evolution, even the most improbable events become certainties. Vacuum decay would be the ultimate cosmic reset button. Everything that has ever existed, every star, planet, and living being, would be eradicated and supplanted by a universe governed by fundamentally different physics. No trace of our present reality would endure, not even the memory of its existence. Some theories propose that vacuum decay might have occurred multiple times throughout our universe's history, each transition generating new regions with distinct physical laws. We might inhabit just one bubble among many, encompassed by realms where the rules of existence are utterly alien. In the universe's infancy, mere moments after the Big Bang, when its size was less than an atom and its density surpassed that of a neutron star's core, minuscule density fluctuations might have collapsed, giving rise to black holes. These behemoths, primordial black holes, would be more massive than mountains yet smaller than atoms. Their gravitational fields, incredibly intense, would warp space-time on scales imperceptible to human eyes. Unlike black holes originating from collapsing stars, primordial black holes could possess any mass. Some might weigh as little as a paperclip, others could dwarf our sun. The smallest would be quantum objects, where the peculiar laws of quantum mechanics clash with the unwavering authority of general relativity in ways we only partially comprehend. A primordial black hole, with the mass of a mountain, would be smaller than a proton, yet exert a gravitational field millions of times stronger than anything achievable on Earth. Space-time around such objects would be contorted into unimaginable geometries, generating regions where the familiar notions of distance and duration become meaningless. These microscopic titans would rank among the universe's most violent entities. According to Stephen Hawking's calculations, black holes emit radiation and gradually evaporate. The smaller the black hole, the faster its evaporation, and the more cataclysmic its demise. A primordial black hole with the mass of a large asteroid would explode with the energy of millions of hydrogen bombs. The final moments of a small primordial black hole's existence would be spectacular beyond human comprehension. As it shrinks to subatomic dimensions, its evaporation rate accelerates exponentially. In its last second, it would release more energy than our sun generates in an entire year, all concentrated in a point smaller than an atomic nucleus. If primordial black holes exist in significant numbers, they could resolve one of cosmology's most enduring enigmas, the nature of dark matter. These unseen objects would exert gravitational influence without emitting light, precisely mirroring the properties astronomers observe in dark matter throughout the cosmos. The quest for primordial black holes has driven scientists to explore some of the cosmos's most extreme environments. As these objects traverse stars, they would heat the stellar material, causing detectable brightness variations. Collisions with neutron stars might trigger observable gravitational wave signals. Some primordial black holes might have grown over cosmic time by accreting matter and merging with their counterparts. These entities could now be lurking unseen in interstellar space, invisible predators awaiting encounters with matter they can consume. Their gravitational lensing effects might occasionally distort and amplify light from distant stars. The most massive primordial black holes could have acted as seeds for the supermassive black holes we observe at galactic centers today. This would explain how such enormous black holes could have formed so early in the universe's history, when normal stellar evolution was still in its nascent stages. Before the universe was even a single second old, space itself underwent the most ferocious expansion in all of cosmic history. In a period briefer than the time light needs to traverse a proton, the universe swelled from dimensions smaller than an atom to a size exceeding that of a grapefruit. This event, termed cosmic inflation, stands as the most potent force ever unleashed, stretching space at a velocity surpassing the speed of light and laying the foundation for all that followed. During inflation, space expanded by a factor of at least 10 to the 26th power in a mere 10 to the negative 35th power seconds. To illustrate, envision a solitary atom abruptly growing larger than our solar system in less time than light requires to cross that atom's width. This expansion was so breathtakingly rapid as to defy human comprehension. The driving force behind this inflation was a quantum field called the inflaton, which permeated all of space with an immense energy density. Unlike ordinary matter, this field possessed the peculiar characteristic of generating more energy as space expanded, behaving like a cosmic fuel with an inexhaustible supply. The more the universe grew, the more energy became available to propel further expansion. Inflation resolved several fundamental conundrums that had perplexed cosmologists for decades. Prior to inflation, the universe would have been replete with exotic particles and topological defects, which should remain observable today. The rapid expansion, however, stretched these objects to dimensions exceeding those of the observable universe, effectively concealing them beyond our cosmic horizon. The expansion during inflation was so extreme that regions of space initially in contact were stretched far beyond any possibility of interaction. This explains why the cosmic microwave background radiation displays nearly identical temperatures across all directions. Even though these regions could never have exchanged energy after the expansion commenced, quantum fluctuations within the inflaton field during inflation were stretched to cosmic scales, generating the density variations that would later evolve into galaxies and galaxy clusters. These minuscule ripples in the fabric of space-time became the seeds of all large-scale structure in the universe, from the smallest stars to the largest superclusters. The energy involved in cosmic inflation was truly staggering. In just an infinitesimally small fraction of a second, the inflaton field released more energy than has been produced by every star in the observable universe over the past 13.8 billion years. This energy was channeled into creating new space and filling it with the matter and radiation we observe today. When inflation finally concluded, the inflaton field decayed into ordinary matter and radiation, reheating the universe to temperatures exceeding 10 to the 28th power degrees. This was sufficiently hot to create and destroy particles at rates that would render the cores of even the most massive stars comparatively frigid. Some theories propose that inflation was not a singular event, but rather an eternal process continuously generating new regions of space-time beyond our observable universe. In this scenario, our entire cosmos might be merely one bubble within an infinite multiverse, where new universes are perpetually born through inflation. At the heart of a dying star, spinning at 1,000 revolutions per second, magnetic fields 1 trillion times stronger than Earth's are poised to unleash unimaginable destruction. This is a magneto-rotational supernova. The synergy of extreme rotation and magnetic power generates explosions surpassing even the most potent gamma-ray bursts, forging magnetic fields so intense they could shatter atomic nuclei from thousands of miles away. When the universe's most massive stars expire, some possess magnetic fields comparable to those of magnetars. If such a star is also rapidly rotating when its core collapses, the conservation of angular momentum accelerates the collapse, much like a figure skater's pirouette speeds up as their arms are drawn inward. As the stellar core contracts from the size of Earth to just 12 meters across, its rotation rate increases millions of times. The magnetic field lines embedded within the collapsing plasma become twisted and amplified, reaching strengths nearing physics' theoretical limits. These fields become so potent they influence the fabric of space-time itself. The magnetic pressure within these extreme fields surpasses the pressure inside atomic nuclei. Field lines stretched to their breaking point store immense energy. When these magnetic structures destabilize and reconnect, they release this stored energy in violent magnetic explosions that dwarf solar flares. The combination of rapid rotation and extreme magnetic fields creates a cosmic dynamo, unparalleled in the universe's power. Charged particles trapped within these fields are accelerated to energies far beyond those achievable in our most advanced particle accelerators. Individual protons gain sufficient energy to fission atomic nuclei through sheer kinetic impact. These magneto-rotational explosions can launch jets of magnetized plasma at velocities approaching the speed of light. Unlike jets from ordinary gamma-ray bursts, these magnetically driven outflows remain focused across intergalactic distances, creating beams of destruction capable of sterilizing planets from millions of light-years away. The magnetic fields generated during these explosions are so powerful they affect the vacuum of space itself. At field strengths exceeding 10 to the 15th power Gauss, the quantum vacuum exhibits birefringence, splitting light into distinct polarizations and producing optical effects unlike any other in the universe. Space itself transforms into a type of cosmic crystal with directional properties. Matter subjected to these extreme magnetic fields experiences seemingly impossible effects. Atoms elongate into needle-like shapes, aligned with the field. The chemical bonds holding molecules together are twisted and distorted beyond recognition. Even the fundamental particles composing atoms exhibit strange new behaviors. The energy released by a magneto-rotational supernova can exceed that of a normal supernova by hundreds of times. The explosion synthesizes exotic isotopes, impossible to create under any other conditions, forging elements that exist for mere seconds before decaying into more stable forms. These cosmic alchemical laboratories produce materials that redefine the boundaries of nuclear physics. In the expansive halos encircling each galaxy, an unseen substance surpasses the total mass of all stars by a factor of 5 to 1. This dark matter experiences gravity's influence, but interacts with nothing else within our current understanding, forming a hidden universe that shapes cosmic structures while remaining completely undetectable to our senses. However, if dark matter particles ever encounter their antimatter counterparts, the result could be explosions dwarfing even supernovae in intensity. Dark matter particles, if they are their own antiparticles, would undergo complete annihilation upon collision, converting their entire mass into pure energy. According to Einstein's renowned equation, a single kilogram of dark matter undergoing this annihilation would release energy equivalent to 21 million tons of explosives, representing the most efficient energy source theoretically conceivable. In the dense cores of galaxy clusters, where dark matter concentrations reach their zenith, these annihilation events could generate cascades of high-energy particles and gamma rays. The released energy would eclipse the combined output of all stars within the cluster, producing radiation so intense that it could be detected from distances of billions of light-years. Some theories propose that dark matter particles could possess significantly greater mass than ordinary protons and neutrons, potentially containing the energy equivalent of hundreds or thousands of hydrogen atoms compressed into a single particle. When such massive particles annihilate, they would generate particle showers of extraordinary energy, initiating cascade reactions that produce exotic particles unlike any found elsewhere in nature. The annihilation process could create pairs of photons, including visible light. These gamma rays would bear the signature of dark matter destruction, offering a direct means of investigating the properties of this enigmatic substance. The most energetic annihilation events could produce photons with energies approaching the Planck scale, where quantum gravity effects become significant. If dark matter annihilation preferentially occurs in high-density regions, it could trigger feedback mechanisms that influence the distribution of matter on cosmic scales. The released energy could heat nearby gas, preventing its collapse to form new stars. Entire galactic regions might be rendered sterile by the radiation emanating from dark matter annihilation in their central regions. In the extreme environment near black holes, where dark matter densities attain extraordinary levels, annihilation rates could become so substantial as to contribute significantly to the overall energy output. These events might generate observable signatures in the form of high-energy neutrinos or gamma-ray flares, potentially revealing the presence of concentrated dark matter. Certain theoretical models predict that dark matter annihilation could initiate chain reactions, where the released energy creates conditions conducive to further annihilation events. These cascading annihilations could deplete entire spatial regions of their dark matter content, leaving behind cosmic voids filled with high-energy radiation. The quest for signals of dark matter annihilation has prompted astronomers to study the universe's most extreme environments. Galaxy centers, where dark matter densities reach their peak, are prime locations for detecting the characteristic gamma-ray signatures of annihilation. The current absence of clear signals suggests either that dark matter does not self-annihilate, or that this process occurs far less frequently than initially hypothesized. Deep within the vast expanse of space, protons are propelled to energies far surpassing anything achievable on Earth. These cosmic ray particles traverse the galaxy at 99.9999% of the speed of light, each carrying energy equivalent to a baseball hurled at 60 miles per hour, yet concentrated within a single atomic nucleus. The cosmic engines generating these particles operate on scales and with efficiencies that render our most advanced technologies seemingly rudimentary. The most energetic cosmic rays detected on Earth possess energies exceeding 10 to the 20th power electron volts, more than 10 million times the energy attainable in the Large Hadron Collider. A single such particle holds sufficient energy to illuminate a small bulb for a fleeting instant, all compressed into an object smaller than a proton. Upon striking Earth's atmosphere, these particles initiate cascades of secondary particles, triggering detectors spanning thousands of square miles. The cosmic accelerators responsible for these phenomenal particles remain one of astrophysics' most enduring enigmas. While supernova shockwaves can accelerate particles to high energies, they cannot account for the most extreme cosmic rays. The electric fields necessary to accelerate particles to such energies would need to extend across distances of millions of light years, maintaining voltages exceeding 10 to the 20th power volts. Active galactic nuclei, powered by supermassive black holes, represent the most plausible cosmic accelerators. The magnetic field surrounding these objects can store immense amounts of energy, releasing it in sudden bursts that accelerate particles to relativistic speeds. The jets emanating from these black holes create natural particle accelerators millions of light years in length, dwarfing any human-made machine. As cosmic ray particles journey through space's magnetic fields, they are deflected and scattered, making it virtually impossible to trace them back to their origins. Only the most energetic particles, those with energies exceeding 10 to the 19th power electron volts, travel in near straight lines through galactic magnetic fields. These ultra-high energy particles provide our sole direct probes of the universe's most extreme acceleration processes. The interplay between cosmic rays and magnetic fields generates some of astrophysics' most spectacular phenomena. As these particles spiral around field lines, they emit synchrotron radiation, a glow spanning the electromagnetic spectrum. Our galaxy's radio emission is largely generated by cosmic ray electrons spiraling through the Milky Way's magnetic field. Cosmic ray acceleration can proceed through multiple mechanisms, each operating on different scales and yielding particles with distinct energy spectra. Shockwave acceleration occurs when particles repeatedly traverse shock fronts, gaining energy with each crossing. Magnetic reconnection can impulsively accelerate particles when twisted field lines abruptly snap and rearrange. The most extreme cosmic ray events might involve entirely different acceleration mechanisms yet to be discovered. Some theories propose that the decay of exotic particles, remnants from the Big Bang, could produce cosmic rays with energies surpassing anything achievable through conventional acceleration. These hypothetical particles could be relics of physics beyond the standard model. Cosmic ray interactions with interstellar gas and dust create secondary particles, including gamma rays, neutrinos, and positrons. These secondary products convey information about both the cosmic rays themselves and the environment they traverse. The study of cosmic ray secondaries has revealed the composition and structure of the interstellar medium in ways unattainable through direct observation. In the seemingly empty expanse between atoms, between planets, between stars, the quantum vacuum teems with unseen activity. Virtual particles blink into being, only to vanish in instants too brief for direct observation. Yet these quantum fluctuations, operating at the minuscule scale of the quantum realm, possess sufficient energy to fuel the entire observable universe and may ultimately dictate reality's destiny. The quantum vacuum, far from being truly empty, is filled with zero-point energy, a persistent energy present even at absolute zero temperature. Each cubic centimeter of space harbors virtual photons, electron-positron pairs, and myriad other particle combinations that momentarily borrow energy from the vacuum, repaying their debt before quantum mechanics detects the breach. This ceaseless creation and annihilation of virtual particles generates an energy density that, if harnessed, would dwarf the mass energy of all matter within the universe. Calculations indicate that the energy density of quantum vacuum fluctuations should be 10 to the 120th power, greater than the universe's observed energy density. This immense discrepancy, termed the cosmological constant problem, stands as one of theoretical physics' greatest challenges. Were these calculations accurate, space itself would be so energetically unstable that atoms could not exist. However, quantum vacuum fluctuations produce verifiable effects, validating their reality. The Casimir effect illustrates this. Two closely positioned metal plates experience a mutual attraction due to the pressure exerted by virtual particles. The space between the plates excludes certain virtual photon wavelengths, creating an imbalance that generates a minuscule yet detectable force. Near the event horizons of black holes, virtual particles can transition into real particles via a mechanism discovered by Stephen Hawking. One member of a virtual particle pair may fall into the black hole while its partner escapes, leading to the black hole's gradual evaporation. This Hawking radiation signifies the conversion of vacuum energy into real particles, underscoring the immense power residing within quantum fluctuations. In the early universe, quantum vacuum fluctuations were amplified to cosmic dimensions during the inflationary epoch. These microscopic energy variations became the seeds of all large-scale structures, growing under gravity's influence to form the galaxies and galaxy clusters we observe today. Every star, planet, and living organism owes its existence to quantum fluctuations that occurred when the universe was smaller than a single atom. Certain theories propose that our entire universe originated from a quantum vacuum fluctuation, a fleeting deviation from nothingness that somehow became enduring. In this scenario, the Big Bang itself would not mark the beginning of time, but rather the moment a virtual universe became real, borrowing energy from the quantum vacuum, an energy it has been repaying through cosmic expansion ever since. The potential energy residing within quantum vacuum fluctuations might be harnessed by advanced technologies capable of manipulating the very fabric of space-time. Theoretical methods for extracting this vacuum energy involve generating negative energy densities or controlling the boundary conditions governing which virtual particles populate a specific spatial region. If successful, harnessing vacuum energy would yield a virtually limitless power source, ubiquitously present throughout the cosmos. A device as small as a coffee cup could potentially generate enough energy to sustain human civilization for billions of years, rendering all other energy sources instantly obsolete. Beyond the observable universe's boundary, further than the most distant galaxies we can ever hope to detect, lies a phenomenon eclipsing all previously encountered cosmic forces. Should the multiverse exist, our universe, with its supernova, black holes, and gamma-ray bursts, would be merely a single bubble in an infinite ocean of realities, each possessing unique physical laws, a distinct history, and its own ultimate fate. In the eternal inflation model, our Big Bang was not singular. Rather, it was one among countless explosions continuously occurring across higher dimensional space. New universes are perpetually born as quantum fluctuations trigger inflation in false vacuum regions, generating an ever-expanding network of cosmic domains stretching infinitely in all directions. Each universe within this multiverse could possess entirely different fundamental constants. In some, gravity might be stronger or weaker, altering star and galaxy formation. Others might exhibit a different electromagnetic force strength, rendering atoms impossible or creating matter with unimaginable properties. The strong nuclear force could be modified, preventing nuclear fusion or enabling elements non-existent in our reality. The total energy contained within an infinite multiverse would, quite literally, be infinite, representing the ultimate cosmic power. Every possible configuration of matter and energy, every conceivable physical law, and every potential history would exist somewhere within this vast ensemble of realities. The capacity to create infinite universes with infinite diversity signifies the absolute zenith of cosmic power. Some multiverse regions might contain universes expanding eternally, while others might collapse upon themselves, in big crunches mirroring their Big Bang origins. Still others might oscillate between expansion and contraction, resulting in endlessly repeating cyclic cosmologies. The diverse cosmic destinies within a multiverse would encompass every possibility permitted by mathematics and physics. Under certain interpretations of quantum mechanics, the multiverse comprises all possible outcomes of quantum measurements, coexisting simultaneously in parallel realities. Whenever a quantum event with multiple potential results occurs, the universe splits into separate branches, each embodying a different outcome. This quantum multiverse would perpetually expand as new possibilities materialize. The anthropic principle suggests that we observe our universe's specific combination of physical constants because only this combination allows observers like ourselves to exist. In a multiverse containing all possible combinations of physical laws, conscious beings would inevitably find themselves in universes capable of supporting consciousness, regardless of the unlikelihood of such universes. If inter-universal communication were feasible, it would unlock access to unlimited knowledge and resources. Technologies developed in universes governed by different physics might be incomprehensible to us, yet could offer solutions to problems we cannot even envision. The exchange of information across the multiverse would represent the ultimate expansion of scientific knowledge. The ultimate fate of the multiverse might involve the consumption of false vacuum regions by expanding bubbles of true vacuum, creating a cosmic selection process where only the most stable vacuum states endure long-term. This could culminate in a final state where all of reality converges upon a single set of physical laws, ending the multiverse's infinite diversity. We've traversed the expanse from the quantum realm to the hypothetical infinite multiverse, encountering forces that challenge our very definition of reality. From the strong nuclear force, the glue-binding atoms, to the potential for endless universes birthing and perishing in an eternal cycle, we've observed power on scales beyond comprehension. The most striking revelation is not that the universe contains power, but that it is power. Every atom composing your body exists due to unimaginable forces holding it intact. Every star, illuminating the cosmic void, burns because nuclear forces transmute matter into pure energy. Every galaxy's rotation across billions of light-years is a testament to gravity and dark energy locked in perpetual conflict. But perhaps the most profound understanding is our inextricable link to these cosmic forces. We are their direct offspring. The calcium in our bones was forged in supernovae. The iron in our blood was scattered by dying stars. The gold in our jewelry originated from the violent collision of neutron stars, events that shook space-time itself. We are, quite literally, stardust, assembled by forces capable of creating and destroying entire worlds. And yet, here we stand, conscious beings capable of contemplating our cosmic origins. This proves that the universe's greatest power might not be destruction, but its capacity for complexity, beauty, and ultimately, awareness. 13.8 billion years, the universe has labored to create the conditions for your existence. Every force we've explored, from quantum fluctuations to galactic collisions, played a part in bringing about this moment, allowing you to comprehend your place within the cosmic narrative. What constitutes the universe's most potent force? Perhaps it's not a singular entity, but the universe's boundless creativity, its ability to transform simple hydrogen into stars, stars into heavy elements, elements into planets, and planets into the stage for life and consciousness capable of contemplating the very forces that birthed them. When you next gaze upon the night sky, remember that you are witnessing the ongoing struggle between the cosmic forces that shaped all you perceive. And remember that you, composed of stellar remnants and quantum dreams, are not merely a spectator to this cosmic drama. You are one of its most remarkable achievements. The universe's most potent force may well be its capacity for self-awareness, achieved through beings such as ourselves. By understanding cosmic power,